No mai haere mai, tēnā koutou, tēnā koutou, tēnā koutou katoa, inga reo, inga mana, inga waka, tēnā koutou, tēnā koutou, tēnā koutou katoa. So I'm the Vice-Chancellor of Victoria University of Wellington, Te Herenga Waka, and my name is Nick Smith, and it's my great pleasure this evening to welcome family and friends, distinguished guests, academic and professional colleagues, students, and our wider community to the inaugural lecture of Lisa Orloff Clark, Professor of Mathematics. Professor Clark moved to Aotearoa, New Zealand from the United States in 2011 before joining us here at this university in 2017. She's completed her entire tertiary education before that process in the US, BA in Mathematics, cum laude, and then a PhD in Mathematics from Dartmouth College in New Hampshire. And I think even more extraordinary than those achievements by themselves is, as she describes it, the unconventional journey to her PhD, and specifically welcoming 2 of her 3 children into the world during those years. And for anyone who has done a PhD, the capacity to focus myopically on a particular problem at the same time as bringing small children into the world is an extraordinary feat, and it's probably definition of a Renaissance person in and of itself. She says that it was her support system that enabled her to preserve her studies during that period, and as part of that, her interest in mathematics, I think in her words, stems from the ability to distinguish between right and wrong with mathematical equations, and the beauty that algebra can bring to giving clarity and to be able to manipulate abstract ideas and then find things out that you otherwise wouldn't see. I think often the discipline of pure mathematics and algebra in particular doesn't get credit for how creative it is and how innovative it is in those problem-solving skills. And I think that's why it's going to be very interesting to hear Professor Clark's lecture tonight. She tells me that originally she planned to pursue pre-med, but found greater success in mathematics courses. Growing up in a small town, it was unheard of to have a career in mathematics. But she says the people who have offered her support every step of the way have been key to that process. And we at this university are absolutely thankful that she has chosen to come and share her talent and expertise and experience here at Te Herenga Waka. She didn't go down the pre-med route, and she has made enormous contributions in her field as she is. She's also played a significant role in professional development of her colleagues, which I think befits the status and the rank of professor at this university. She has had leadership roles as the head of the School of Mathematics and Statistics. She's also had previous roles as the deputy head and the program director for mathematics and statistics. And during that time has continued to sustain high quality teaching and a research reputation in the field of algebra and analysis that is the envy of anybody in this process. In 2017, she received New Zealand's Mathematical Society's top prize, the Carman Prize, for the very best paper. In this lecture, Professor Clark will explain abstract and sometimes complex mathematical subjects in a manner that is easy for everyone to grasp, and that is a skill in itself. She has also promised, and this is what I'm excited about, a bit of theatrical entertainment. She has a minor in musical studies, and I'm sure that will assist in the entertainment side of things. But with no further ado, it is my enormous pleasure to introduce Professor Lisa Orloff Clark to give her inaugural lecture here at Te Herenga Waka, Victoria, University of Wellington.
Thank you. Tēnā koutou, tēnā koutou, tēnā koutou katoa. I'm a bit overwhelmed, but thank you so much for being here. I have a lot of gratitude for the opportunity to be here and present to you today. So let's just dig right in. So I'm going to divide my lecture today into 3 distinct parts. So the first part, I'm going to talk about the subject of what does a mathematician look like. And then I'm going to do some concrete mathematics in the second 2 parts. The second part will be some analysis, which is a branch of mathematics, and the third part will be some abstract algebra. So this first question, what does a mathematician look like? So if you would have asked me this question when I was a kid, as Nick said, I grew up in a rural place. I just wasn't exposed to mathematicians. I wouldn't have even realized that was an actual career path for a person. And I think I probably would have just said a generic kind of nerd. And a shout out to my daughter Josie, who encourages me to use this nerd emoji in my research lectures. So in preparation for this lecture, I Googled mathematician to see what Google thought it looked like. And if you don't put any adjective in front of the mathematician, you get a similar looking sort of thing. So for example, slightly blurry, here's a website that claims some of the greatest, it doesn't say some of, the greatest mathematicians of all time. And so there's some people. So there's Isaac Newton, Gauss, Euler, Archimedes, Riemann, Euclid, Poincaré, Lagrange, Hilbert, Leibniz, Grothendieck, and Fermat. So all these greatest mathematicians of all time are men from Europe, in fact. Some more mathematicians as I was Googling around. Here's some, let's see if you can recognize some of these 20th century mathematicians. So here's one. Anybody know who that is? That is Hardy. This one? That is Bertrand Russell. This one's more obscure. This is Stefan Banach. This guy, I put this one on here because I wanted everybody to be able to recognize at least one of them. Who's that? That's, of course, Albert Einstein. He's not really a mathematician, he's sort of a physicist, but there's lots of overlap between math and physics. And actually, these pictures I picked for a particular reason. It entertains me that these are these formally posed, professionally taken looking photographs where they're all smoking pipes. Or Banach, it looks like a cigar. But seriously, the question of what does a mathematician look like is a bit of a silly question because a mathematician is a person. People look all sorts of different ways. There are great mathematicians from all over the world that come in all different gender identities, and so they're not all men from Europe. But it is true that mathematics has historically and still today suffers from a lack of diversity. And from my personal experience, I think that's from lack of opportunities and perhaps barriers that exist, and also from assumptions that people make about what a mathematician is or does. And so in particular, people don't expect a mathematician to look like me. I have found this over my career, like the kind of assumptions and comments I get from people. So I won't go into my whole how did I get here today. It's kind of a boring story, but I'll tell you sort of how I got into it. As Nick said, I did want to go pre-med, but it's mostly because I came from, again, you could almost call where I grew up kind of backwoods. Like, that we had a school holiday on the first day of deer hunting season. There were only maybe like 5 career paths I knew about, so pre-med was one that, if you're ambitious and you want to do some good, maybe you'll go and be a doctor. But I did have good math teachers in high school. So I did get some training. I wasn't particularly interested in it. It was sort of drudgery, but I got the training I needed. And also, in my last year of high school, I actually had who was a great mathematician to me, a teacher, Dr. Petrella. He actually had a PhD, who showed me a little bit of what mathematical thinking really looked like. And so I sort of became a little bit more like, oh, mathematics is cool and fun and beautiful. But I still didn't have it in mind as a career path. So I knew I was going to university, and so I had an incredibly supportive family. I had access to public loans to get me to university, went to study pre-med, but the liberal arts system in the US means everybody has to take some mathematics. So I took Calc 1, and that's the beginning of how I got to be here today. So there I am. Yeah, I don't have glasses on right now, but in my natural state, I'm actually incredibly nearsighted, so that's not so far off. And to help me look the part today, one of the great mathematicians here at Te Herenga Waka, who also happens to be a man from Europe, has lent me a little... Oh. Okay. But as I said, I think there are mathematicians maybe out there who haven't received training, who might not realize it's a career path for them. So I want to just talk a little bit, let's step back before we decide what a mathematician is. What is mathematics? It's a very difficult question to really answer. And the first thing that pops into my head when I hear that question is this quote. So a Supreme Court justice in the 1960s in the US was asked his definition of pornography. And he said, I don't know if I can define it, but I know it when I see it. Now, this I think is problematic because a lot of people think they know mathematics when they see it, but in fact, I don't think they do. Mathematicians probably do. But I think there are some incorrect stereotypes of what mathematics is. So, mathematicians aren't necessarily good at arithmetic. I myself am not. I'm fine, but it's boring, and I can't multiply large numbers together in my head very fast. I'm happy to reach for a calculator. This is a big one. So mathematicians don't necessarily have good spatial skills. There are some mathematicians who do, and in fact, I feel like there are some testing to test for mathematical aptitude that are all about spatial skills. And I feel like they don't quite get to what they need to. But as I said, I don't have good spatial skills. I am a person who gets lost more than I find my way. I am a little miss, no sense of direction. I'm a little professor now, no sense of direction. So this is the Google version of the Oxford English Dictionary definition of pure mathematics. It sort of is entertaining. It says the abstract science of number, quantity, and space as abstract concepts. So it says abstract twice, which is probably sort of appropriate. But I don't mind this definition so much because it's not exactly number, quantity, and space. It's sort of something about them that's the science of them or the abstraction of them. I also found a New Yorker article called What is Mathematics by Alec Wilkinson. And it sort of highlights the two things that appeal to me most about mathematics. The first is that it's precise and unambiguous. So Wilkinson says, mathematicians live within a world that is certain. The rest of us, even other scientists, live within one where what represents certainty, and so far as we can tell, this result occurs almost all the time. Because mathematics' insistence on proof, it can tell us within a range of what it knows, what happens time after time. So it's concrete, precise, but it's also the language of the universe. As precise as mathematics is, it is the most explicit language we have for the description of mysteries. Being the language of physics, it describes actual mysteries, things we can't see clearly in the natural world, but suspect are true and later confirm, and imaginary mysteries, things that only exist in the mind of mathematicians. So what is mathematics to me, or what things remind me of mathematics? So before I go into that, I want to say as a caveat, this is my perspective on what mathematics is to me. Mathematics is a highly collaborative discipline, and any mathematician you talk to will probably have different perspective on what mathematics is to them. There are going to be mathematicians who can multiply large numbers together in their head. There are going to be mathematicians who have incredibly good spatial skills. So what is it to me? Well, before I do that, just to enhance this diversity in mathematics is where great things happen. So again, an article from Scientific American by Catherine Phillips. Diversity in all things, but especially in mathematics, enhances creativity. It encourages the search for novel information and perspectives, leading to better decision-making and problem-solving. Okay, mathematics to me. So as I said, I don't have good spatial skills, but it doesn't mean I don't have any spatial awareness. I do have a spatial sense, it's just disoriented. So I don't know if you recognize this picture, what it's from. It's from the show Stranger Things. In Stranger Things, there's the regular old universe, and then there's this parallel universe where this kid gets trapped, and it's called the Upside Down. And I feel like I'm not always sure which one I'm in. Like I don't know my left from my right, that kind of thing. But I do have an awareness spatially. And sort of an example of this, so one of my children, Adair, who, he's not here tonight, but I want to tell a story. So when Adair was young, maybe around 9, I was trying to describe to Adair what clockwise meant. So I'm like, you just go around the direction of the clock. And Adair said, yeah, but how do I know if the clock is facing me or if I'm facing the same direction as the clock? That's a mathematician. All right. Puzzles. So most mathematicians, from my perspective, like all sorts of puzzles, like jigsaw puzzles, Sudoku puzzles, crossword puzzles. And I think this is connected to mathematics in a pretty sophisticated way. So for example, I don't know if you're familiar with Bletchley Park. So in World War II, there was this top secret code-breaking agency called Bletchley Park that basically hired a bunch of mathematicians to try to crack the Enigma code of the Germans. And again, they were code breakers, cryptography, which is a branch of mathematics. And how did they recruit people? Well, they went through the usual channels of universities and things, but they also did this cryptic crossword competition. So I think this is the actual cryptic crossword they used in the Telegraph. And they had this competition, and they brought people in to do it. And apparently anybody who could do it in 12 minutes or less, like where they were told they were a winner. But then they were contacted later by the government and said, we're invited to participate and become mathematicians in Bletchley Park. So it wasn't necessarily those trained in mathematics that they wanted. And Bletchley Park to me is a symbol of how diversity really does make great things happen. So not only did the work they did there was what led to the Allies' success, or it's one of the pieces that led to the Allies' success in World War II, but it also is incredibly famous now, ran by Alan Turing, because it's where sort of the first digital computers were developed. So out of the minds of mathematicians came this thing that has now changed the world. And Bletchley Park, 75% of the staff there were women, actually. Music. So this is a little bit, again, I know great mathematicians who aren't into music very much, but for me, and for lots of people, well, stepping back, it's pretty common knowledge that there's a pretty big overlap between musicians and mathematicians. And you'll maybe see in a bit that my musical performing ability isn't that high, but I've always had a knack for music. From the time I was a young child, I've had a knack. And it's similar. I feel like it's coming from the same place as my knack for mathematics. I feel like they're deeply connected. And these are some quotes of just people who, I tried to find some succinct quotes online. That first one, I don't know if that's really Pythagoras, just lots of people online seem to say it is. So there's geometry in the humming of the strings. There's music in the spacing of the spheres. Another one is Leibniz, one of the greatest mathematicians of all time from earlier. Music is the pleasure the human soul experiences from counting without being aware that it is counting. Thelonious Monk, jazz musician. All musicians are subconsciously mathematicians. Stravinsky, classical composer. Musical form is close to mathematics. Sylvester, a mathematician. This is my favorite one, probably. The musician feels mathematics. The mathematician thinks the music. Music, the dream. Mathematics, the working life. And sort of related to music, I think there's kind of a nice metaphor of what a mathematical result looks like. So when we do mathematics, pure mathematics, we start with axioms and definitions and previously established results, and we carefully put the pieces together part by part to forge something new. And it's very much like a symphony, like the instruments all coming together to create something new and beautiful. I was going to play a little thing for you, but I decided I'm kind of time conscious and I didn't want to keep you too long. But if you have time, go listen to Bach's Little Fugue in G minor, the orchestral arrangement, in that it's a symphony, so it's this combination, but it's also building a particular melody layer by layer in a way to create something beautiful that really reminds me of what mathematics research looks like. And they're not exactly the same, of course. Like music everybody can sit and listen to. Mathematics is kind of written down, so mathematicians try to speak to each other, so it's a lot more abstract, it's different. But mathematics is the language of the universe, and these things we write down are little fugues describe things like the motion of light, and the sun, and the stars, and the earth, and the moon, black holes, gravity, plate tectonics, ocean tides and waves, air currents, storms, nuclear reactions, radioactive decay, I'm going to read it all, chemical reactions, electric circuits, crystals, bubbles, genetic inheritance, birdsong, evolutionary trees, population growth, heartbeats, fluid flow, image processing, skyscrapers, rocket ships, profit margins, the stock market, the economy, traffic patterns, train schedules, delivery routes, the spread of disease. And our modern digital world, as I said, grew out of the minds of pure mathematicians. And this is just off the top of my head. And so what I don't think people realize is some training in mathematics means you can contribute in any one of these areas. So in preparation for this lecture, I went looking around for images. What does a mathematician look like? These are people that speak the language of the universe. I felt like it was something more like this. All right. Shall we get into some actual mathematics now? I'm sure you're all excited. So some analysis and then some algebra. And kind of a metaphor, like some singing and some dancing. Okay, so analysis. Analysis is a pretty old subject in mathematics, and it's all about limits. So 1700s is where it was formalized. So limits are things that happen when you go to infinity or when you go to zero, but not getting there. So I'm going to start out by describing something called Zeno's paradox. I'm going to get to experience my lovely handwriting. So Zeno's paradox is, Zeno's an ancient Greek philosopher. Usually this is told with Achilles and a tortoise, but today I'm going to tell it with an ant. This is an ant named Antonia. They like to be called Ant. And is walking along a 2-meter-long path at a constant speed. And I actually mean, I don't know if you can see my little cursor there. It's actually walking along a longer path with a 2-meter section marked off, so it continues. And so Zeno might ask, well, let me see, there's Antonia, ant. Zeno asks the question, does the ant get to the other side if they're walking along at constant speed? I could have somebody get up and demonstrate walking, but the answer is obviously yes. The ant gets to the other side. But why is this called a paradox? Well, in order for ant to walk this 2-meter distance, ant must first walk half the distance, which is 1 meter. And then, in order to walk the rest of the way, ant needs to walk half the distance that's left, which is a half a meter. And then ant needs to walk half the distance that's left, and that's a quarter of a meter, etc. An eighth of a meter, a 16th of a meter. I think that's as far as my drawing could do, but this would go on and on. With half the distance left, a 32nd, etc. So does this process, can this be possible happening and ants still get to the other side? That's what Zeno's paradox is about. And again, the ant does get to the other side. This infinite process does happen. Analysis exists and anytime anything moves. So what is the mathematics of Zeno's paradox? We have something called an infinite series. So ant's journey goes 1 meter and then a half and then a quarter. So this is 1 plus a half plus a quarter plus an eighth plus a 16th plus a 32nd and so on. But this infinite list of pluses, we don't actually really know how to add infinitely plus like that. So what we actually mean in formal mathematics, if we do this infinite series listing all these pluses, is a list of the finite pluses and adding more and more as you go. So 1 plus a half, 1 plus a half plus a fourth, etc. And we ask the question, does this list approach a particular number? That is, does the series have a limit? If it does, we say it converges. If it does not, we say it diverges. So this particular list, I won't spend a long time on it. There's sort of a geometric intuition. It's getting half the distance to 2, So it doesn't ever get any bigger than 2. I think that's pretty clear. But there is rigorous mathematics you can do to actually prove that this list converges to 2, meaning it gets arbitrarily close to 2. It doesn't go any bigger, and there's not some distance before 2 that it stays. It gets as close to 2 as you want it to get. And there's quite a famous joke in mathematics that's related to the series. You know this joke? An infinite number of mathematicians walk into a bar. Here's 3 of them. The first 3, these are my colleagues, Becky Armstrong and Yingfen Lin, walking into a bar with me, a kind of an unlikely trio to be walking into a bar, if you know us. But the first order's a beer, the second order's a half a beer, the third order's a quarter of a beer, the fourth order's an eighth of a beer. The bartender stops them and said, "You guys should know your limits," and pours 2 beers. I didn't write the joke. And you'll see there's a subtle sexism, even in mathematics jokes. You guys. All right, so that's that. So I want to go on and do another one. This next one is the one I want to focus on, and I'd like you to all take away some knowledge about this particular series. So this one's called the harmonic series. I keep needing to take a drink, excuse me. So I let you look at it a second. So this time, 1 plus a half plus a third plus a fourth. So what's next? Plus a fifth plus a sixth, etc. And so on. So again, well, hold on. So this is called the harmonic series, and this one also has this beautiful connection with music. I'm not an expert on all these details, but the idea is, so I have this beautiful picture created for me by Sonia Tenrero. If you were to pluck a guitar string, so like this outside blue, dark blue, is the string would vibrate, at the entire length of the string would vibrate, and you'd hear that, but also half the length of the string would vibrate in 2 spots, and you'd hear that, and a third of the length would vibrate in 3 spots, and you hear that. And these harmonics is what makes music actually sound beautiful. It's what makes a particular musical instrument have the sound it has by how much of the harmonic series you can hear. And there is a sense for when things sound dissonant in music, it's when they aren't on the harmonic series. So, okay, let's get back to the mathematics, though. This harmonic series, remember what I said a series is? Like this infinite list of things. So if we're asking whether this harmonic series converges or not, we want to know, does this list 1 plus a half, 1 plus a half plus a third, etc., does that get closer and closer to some number? Now, this is something we teach in our first year, like a second course in calculus, and this is one that often confuses students. But the quick answer that you get is, all right, the numbers you're adding are getting smaller and smaller and smaller. So intuition is that it can't get that big. So let's just play with it a little bit and see. So I've computed some terms here for you. So the first term, 1 is 1. 1 plus a half is 1.5, a third, etc. So I've gone up through 1 plus a half all the way up to an eighth, 2.7, 1878. I've cut them off at 4 decimal spots unless they were exact. So it's bigger than Ant's journey. It goes past 2. It's looking like it might not go past 3. So I went online and I found there's a harmonic series calculator where you can stick in how many terms you wanted to add up. So I did 100. And it's 5.3, so it does get bigger than 3. And then I thought, all right, let's go 1,000. 7, it gets bigger. 1,000,000, it's 14. So I add up 1 plus a half all the way up to 1 over 10 to the 9th, which is a 1 with 9 zeros. It's 21 point something. 10 to the 20th, it's 46 point something. 10 to the 50th, it's 115. 1 over 10 to the 95th, 219. I was hoping to be able to go to 1 over 10 to the 100th, because I know the name of that 10 to the 100th. That's a Google. But I couldn't. The online calculator, this is as far as it could go. I learned a Google from one of my kids, actually. Talia, whose favorite number was a googolplex for a while, which is 10 to a googol power, 10 to the 10 to the 100. People know that number, googolplex? Anyway, so what do you think? Does it look like it's approaching a number? This is sort of mind-boggling. It's a bit counterintuitive. The number 1 over 10 to the 50th, for example, is so tiny, and the terms we're adding are so itty-bitty tiny, yet somehow this seems to keep getting bigger and bigger and bigger. So let's try a different way. That wasn't a proof of anything. That was just, let's do some computations and see what happens. So this is a little bit more formal. So if I compare this harmonic series that I started with, 1 plus a half plus a third, I claim that it's bigger than this other series. So if that list of numbers approaches something, whatever it approaches will be bigger than this one. So this is, instead of 1 plus a half plus a third, it's 1 plus a half. And I replace the third with a fourth, because a fourth is smaller than a third, and add a fourth plus a fourth. And then instead of doing a fifth, a sixth, a seventh, and an eighth, I do an eighth and an eighth and an eighth and an eighth, etc. So the original one is bigger than this one. This one that I have there, if you look at how I've grouped things together, is actually 1 plus a half, plus a half, plus a half, plus a half. That keeps getting bigger and bigger and bigger. That one goes to infinity. So this series does not converge. It diverges. It has no limit. It just keeps growing strong. All right, so that's kind of cool, I think. Let's vary our joke, shall we? An infinite number of mathematicians walk into a bar. The first order is a beer, the second order is a half a beer, the third order is a third of a beer, the fourth order is a fourth of a beer, and so on. What happens? The world eventually runs out of beer. No, it's not a joke, actually. If that happened, that's what would happen. Okay, so as I said, I would like you to take this with you today. I'd like everybody to leave this lecture knowing exactly what the harmonic series is and whether it converges or diverges. But I know I've been lecturing mathematics for quite a long time, and me saying this in a lecture does not mean that it will mean most of you probably won't take it away from today. But sometimes the way we remember things, we can make that happen without even trying if we put it into the lyrics of a song. So I think I'm going to do that for you today. Let's see if my tech is going to work. I've something to tell you. First start with 1, then keep adding.
A 1 over 2, plus a third and a fourth and a fifth, and continue. You've got to make your series harmonic. Diverges, no limit, just keeps growing strong. Make your series harmonic. 1 plus a half plus a third and so on. Does it reach a million? When you keep adding small numbers, goes well past a million to a googolplex and past that number too. You've got to make your series harmonic. Diverges, no limit, just keeps growing strong. Make your series harmonic. 1 plus a half plus a third and so on. You've got to make your series harmonic. Divergence, no limit, just keep going strong. Make the series harmonic. 1 plus a half plus a third and so on. She's got to make her own mathematics. Sing her own special song. Make her own mathematics, even if nobody else sings along. You got to make your theories harmonic. Divergence no limit, just keep growing strong. Make your series harmonic. 1 plus a half plus a third and so on.
So what is the harmonic series? Does it convert to divergent? I think I lost my microphone. Yeah, our timing got a little off there. Sorry about that. But okay, so that was some analysis. Now let's move on to some abstract algebra. So abstract algebra formalizes the notion of symmetry. So I want to describe for you a basic mathematical structure. Quite loud all of a sudden. And so what I'm going to do to describe this is I need 2 symbols. I'm going to use the symbol A and the symbol J, and an operation, which I'm using the symbol diamond. And an operation is a way of combining A's and J's to get A's and J's out. So I need to tell you how to do that, so a description of what this operation does. So it takes A, operation A, equals, so the equal sign, I'm telling you what the operation does. A operation A equals A operation J equals J, J operation A equals J, J operation J equals A. So this basic mathematical structure we could use to model various things. So for example, when you multiply numbers together, positive and negative numbers have different rules. So if I let A be positive numbers, J be negative numbers, the operation be multiplication. When you multiply a positive times a positive, it's a positive times a negative is a negative times a positive is a negative, and the funny one is negative times a negative is a positive. It could also be used to model something a bit more physical, like I could have a piece of paper, and one side is blank, and one side has an X on it, and maybe J is a thing I do to the paper, which is flip it over, and A is don't do anything to the paper. And the operation is just do one after the other. So I'll start at the bottom. If J is flip over, A is don't do anything. So flip over is like not doing anything. Flip over, don't do anything is just flip over, etc. Don't do anything, flip over is flip over. Don't do anything, and then don't do anything. That's not doing anything. This is an example of a structure called a group. It's a small 2-element group. These symbols that I've used in this are completely arbitrary. I could have used any symbol. As long as the description of sort of what this structure does is the same, it gives you an isomorphic group or the same group. And I decided to work a little. I was so grateful that Deirdre Tarrant of the Tarrant Dance Studio helped me explore the possibility of whether it was possible, instead of using symbols, we could do this with movement. So, for example, instead of the symbol A, I could do a movement. And instead of the symbol J, I could have a movement. And I could describe the operation via a movement. And I also could do somehow signify the operation has happened via a movement, so that equal sign could be done via a movement. And then we could describe this actual structure in terms of these movements. So I'll just read them off and we'll see what they look like. So A, operation A. A, operation J. J operation A. And J operation J. Okay, so that is a little combination of movements to communicate the structure of this two-element group. So my research actually involves something slightly more complicated, something called a groupoid. So I'm going to make this example a little more involved, and I'm going to let now there be 4 symbols. I let the dancers select my symbols. So there's an A and a J, and now a heart and a star as well. And I still have an operation, but this time it's something called partially defined. So I'll tell you what that means in a minute. So the way it works on the A's and J's is exactly the same as what we had before. And the way it works on the hearts and the stars is a copy of what we had before, but replacing it with hearts and stars. So let's see this through motion rather than me reading this out. So I could add now a heart. And a star. A few versions. And then we can see what the structure does. Again, it's a copy of what we just saw, but with different movements. So heart operation heart. Ooh. And heart operation star. Star operation heart. And star operation star. Okay, so I revealed this a minute ago. So what does it mean that this operation is only partially defined? So that's how A's go with J's and stars go with hearts, but we're not allowed to combine certain things. So the operation is only defined between certain pairs. So we can't combine any A's and hearts or A's and stars, J's and hearts or J's and stars. So we can see if we can communicate that through movement. So what happens if I do A operation heart? It doesn't work. But what happens if I try star operation J? It doesn't work. So this is an example of a groupoid that is not a group. And so what I would like to do, I've been so excited. Again, these dancers all had to know this precise structure to be able to communicate this dance. So let's have them put it all together with some music. Let's have them perform this groupoid for us. So that was groupoid, the disjoint formed by the Te Herenga Dance Studio. It was so much fun to work with the dancers, and I was so grateful for working with me on this. But I felt like it just sort of scratched the surface of what you could do in combining mathematics and dance. Like, again, all the dancers really, it's the first time I've ever done such a thing, go and do outreachy sort of thing to do mathematics with people, where every single person who had to engage with it and understood what the structure was. And I sort of we chose an algebraic approach, but you could have approached it like trying to figure out if there's a way to get that symmetry approach in there, or you could explore the notion of who's the identities, this is a mathematical term, who are the inverses and that kind of thing. So it's I was very excited about that. So thank you, dancers and Deirdre, for working with me. So I'm afraid the time has come that I'm going to do a tiny, tiny bit of show you what an actual mathematics talk usually might look like. I won't do it for very long, so if you're not mathematically trained, just let it wash over you. So a groupoid, I just want you to see what it actually would look like. A groupoid is like a group, so most mathematicians who have some abstract algebras training would know what a group is. So it's like a group, except the binary operation is only partially defined. So that is, a groupoid is a set with a partially defined associative binary operation such that each element has an inverse, and there's a formal way to define that. So the previous example we just saw was the disjoint union of the two-element groups. And the operation is partially defined because you're only able to compose elements that each live within the same group. It's a very general structure, a groupoid in general, not that particular one, that's a very specific structure. But groupoids are very general structures, while at the same time being tractable. And so what do I do? If I'm going to simplify things a lot, I actually work with topological groupoids, but I'm going to simplify it and just say, suppose you have a finite groupoid. Then the set of functions from the groupoid to the complex numbers is something called the C-star algebra. So this lives in the world of analysis. It involves limits. We study it with analytical analysis techniques. And C-star algebras are the language of quantum physics, and they're not so tractable. Groupoids are tractable. C-star algebras can be quite complicated. So what we do, or what I do in my research, is I connect properties of the groupoid G to properties of the C-star algebra. So this tractable thing, I try to see if we can sort of see things in the C-star algebra from that tractable thing. And I also try to show that this class, the abstract classes of C-star algebras, that we can get groupoid models for them. And one of the things I've done recently is I've helped to establish a new class of algebras where we change the complex numbers here to an arbitrary ring. And that means the structure we create no longer is a thing in analysis, it's a thing in algebra. And so what that does is creates a bridge between analysis and algebra. I've picked a bridge there that's sort of maybe an hour-and-a-half drive from where I grew up, a little bit of home. Anybody recognize that bridge? That bridge is actually called the Rainbow Bridge, but it is not where your pet goes when it passes away. It is in Niagara Falls, and it's connecting the US and Canada. But as I said, I sort of work between my favorite thing to do in research these days is kind of go back and forth, to take something in analysis and see if we can go across this bridge and prove results in algebra, or start with some results in algebra, go across this bridge and prove results in analysis. All right, that's it. That's all the technical talk. I feel like what also I'm excited about today is we've explored a bridge between mathematics and dance. All right, so one last thing. So this is an American term, a pop quiz. Do you know what a pop quiz is? It's sort of a surprise little test that I'm going to give you. As I said, I wanted everybody to come away with this lecture knowing a few things, so I'm going to give you a test here. What is the harmonic series? 1 plus a half plus a third and so on. Does it converge or diverge? Diverge is no limit, just keeps growing strong. Thank you for listening.
Tēnā koutou katoa. I'm Professor Dave Harper, the Dean of the Faculty of Engineering. I also am fairly astounded. I think that was the most unique
and I don't mean that as a euphemism, in a really positive way, inaugural speech I've ever heard from a mathematician. To those of your colleagues in the room who I've done the inaugural thank you for before. So I am absolutely and genuinely delighted, it's not just words on a paper, to give the vote of thanks to Lisa tonight. It was unique and entertaining and informative and all sorts of things that I was looking forward to. And Lisa is dedicated to fostering a more inclusive community within the field of mathematics. She did that quite deftly early on with some of her illustrations. And she does that very actively. I see that in her role as the head of the School of Mathematics and Statistics, through her teaching, the way that she leads the school, and the way that she behaves. She's a very inclusive person, and it's a pleasure to work with her. As a researcher, she challenges the stereotype that women in mathematics are primarily teachers. She also has taught me that she challenges a stereotype that mathematicians are boring. Sorry, I said that, but I'm still coming to terms with some of what we covered tonight. She publishes research and articles of very high quality, international journals. She actively participates in conferences. She's a fantastic mentor for her students. She secures large grants. She does all the sorts of things. She's a fantastic teacher that we expect and we hope for from a professor. So it's a very well deserved role. She's a fascinating person. It wasn't just what she revealed tonight. We were just having a wee discussion before coming in tonight. You don't know where this is going, but you might know. Playing a little game of, what animal would you be? And Lisa just comes straight up, a gorilla. I'm still trying to pass that one a little bit. But so fascinating in many ways. There we go. Let alone the singing ability. You didn't do any dancing, but
yes, I did.
We could do.
Did.
You did. Okay, enough. Today, Lisa explored the fascinating intersection of dance and mathematics, showcasing how diverse approaches to mathematics transcend conventional boundaries. I think we've had a taste of what she's like as a teacher and how engaging she is with the students. As witnessed tonight, there are approaches to mathematics that extend beyond just the formulaic exercises and can really resound with quite a broad spectrum of people. So your unconventional, again in a positive way, teaching style hasn't gone unnoticed by your students, with students hailing you as the best maths teacher ever, quote that I have here. A special thanks to members of the Tarrant Dance Studio and Deirdre for the great performance tonight. Thank you for coming along, enriching our evening even further, and the chorus of singers. And we have a gift, perfectly timed, from them. So thank you to the various support people, again, who have come tonight. Again, I don't think I've ever seen a mathematics talk before that encompassed the formulas, the singing, the dancing, entertainment. But lastly, we all know that families are really important when it comes to helping each other succeed. And so I would also like to acknowledge your family who have supported your career, especially your partner, David, your 5 children, Talia, Adair, Josephine, who's also, I believe, a member of the dance crew, Emma and Zoe, if I've got that wrong, my apologies, but in their unwavering support here tonight and obviously in the development of your career. So once again, thank you very much, Lisa, for your insightful lecture, the entertainment, the valuable contributions to the field of mathematics, and I'd like everyone to join us through in the common room for refreshments. But before we do that, just thank you yet again for a fantastic